Hello there, and welcome to Deep Space Sleep. I'm so glad you're here tonight. Above every city light, beyond the thin blue edge of our sky, there are suns quietly shining, hundreds of them, close enough that their light still whispers to us across the void. They don't rush or compete. They simply burn, patient and steady, keeping time for a universe that never sleeps. The nearest stars form our cosmic neighborhood systems like Alpha Centauri and Proxima, faint red embers and brilliant white beacons scattered just a few light years away. Science can measure their distance, their temperature for their age. But what remains beyond numbers is the feeling of belonging to that same silent expanse. Tonight, we'll drift gently among them through the calm gravity of the sun, past the crimson light of Proxima, and into the quiet brilliance of stars that wait just beyond. Before we begin, let me know in the comments where you're listening from tonight and what time it is where you are. Your words help other sleepy travelers find this calm place among the stars. For now, let your breath slow. Let your thoughts soften. Let's begin. The sun is not just the nearest star, it's the scale by which we measure the rest of the cosmos. Astronomers call the distance from Earth to the sun one astronomical unit, and they use it as a ruler to map everything beyond. When light leaves this immense sphere of fire, it becomes the first bridge between worlds. That light spreads outward in all directions, touching planets, moons, and drifting dust. From its steady pulse, we build the units that describe the galaxy itself, light years. The distance light travels in a year's time. Everything we know about how far and how bright the universe is begins here, with this single, familiar star that rises each morning. When you think of the sun, you're really thinking of a clock made of light, a quiet measurement of how space itself is arranged. Every beam of sunlight you see has traveled a journey through darkness, lasting 8 minutes and 20 seconds. It left the surface of the sun long before it warmed your skin or reflected from ocean waves. Deep inside that light are particles born hundreds of thousands of years earlier, rising slowly from the core through dense layers before escaping into space. By the time a photon reaches you, it's ancient, carrying the signature of nuclear fire from 93 million miles away. Light moves at a constant speed, yet every sunrise is new, a daily arrival from a distant past. The glow we call now is always a gift delayed by 8 minutes of cosmic patience. Inside the sun's heart, atoms live through endless collisions. Every second, hundreds of millions of tons of hydrogen fuse into helium, releasing a steady flood of energy. The process is pure transformation, matter becoming light. That light pushes outward while gravity pulls inward. A perfect balance that has lasted for more than 4 billion years. It's a slow, rhythmic heartbeat, quiet but unstoppable, turning simplicity into warmth. Fusion begins with hydrogen, the simplest atom, and ends with the golden glow that sustains life on Earth. The next time sunlight touches your face, remember, it began as invisible fire, compressed under unimaginable pressure, a whisper from the center of a star that burns not in fury, but in balance. Beneath the calm surface of the sun lies a deep magnetic rhythm that beats every 11 years. Vast loops of invisible force twist through the solar plasma, building tension until they snap and release flares of radiation and light. These magnetic tides give birth to sunspots, dark, swirling regions that mark the sun's changing mood. As one cycle ends, another begins, like breath drawn in and released. The strength of these magnetic fields shapes the entire solar system, bending cosmic rays, sculpting the solar wind, and even brushing against Earth's magnetosphere. The next time you see the gentle green shimmer of an aurora, you are watching the sun's heartbeat reaching across space to dance upon our sky. To touch the sun directly would melt any metal, yet one small spacecraft has dared to reach into its atmosphere. The Parker Solar Probe moves closer than any machine ever built, flying through the outer corona, where temperatures rise to millions of degrees. It moves faster than any object in human history, skimming the edges of solar fire to taste the wind that powers the heliosphere. Sensors measure charged particles, magnetic waves, and the strange silence of near vacuum. In that silence, Parker listens to the sun breathe, recording the soundless rhythm that keeps our world alive. Each orbit brings it nearer, rewriting what it means to explore, and reminding us that even the most distant warmth begins with the courage to draw close. The sun is constantly breathing. From its surface flows a river of charged particles called the solar wind, streaming outward in every direction at hundreds of miles per second. This invisible current fills the solar system, brushing past planets and shaping magnetic fields. When it reaches Earth, it collides with our upper atmosphere, exciting atoms of oxygen and nitrogen until they glow in curtains of green and violet light. Those shifting veils are auroras, the visible footprints of the sun's breath upon our sky. On calm nights near the poles, you can stand beneath them and feel that connection stretching across 93 million miles. The wind that left the sun days ago is dancing silently above your head tonight, tracing light across the edge of our world and far beyond Earth. The same wind touches every planet in our solar family. When astronomers look at distant suns, they see reflections of our own. The sun serves as the template, a cosmic reference point against which all other stars are measured. Its brightness, temperature, and chemical balance define what scientists call solar-type stars. By understanding how our star fuses hydrogen and maintains equilibrium, we can model the life cycles of stars scattered through the Milky Way. The sun's steady glow tells us how light behaves, how magnetism evolves, and how gravity holds creation together. It is both teacher and mirror, showing us the shared structure of the universe itself. Every telescope that turns outward is, in some way, still looking homeward, searching for the familiar heartbeat of our own sun written across the heavens. Among the many families of stars, our sun belongs to a modest class called G-type main sequence stars, often nicknamed yellow dwarfs. The G describes its surface temperature, about 5,800 degrees Kelvin, while main sequence means it burns hydrogen steadily in its core. Despite the word dwarf, it's neither small nor weak. It's larger and brighter than most stars in the galaxy. Its soft yellow hue is simply the balance between hotter blue and cooler red light, blending into the golden white we see in our sky. From this classification, astronomers map interstellar populations, sorting stars by color and mass, tracing how each one evolves. In knowing its place on this great diagram of life and light, we understand not just what the sun is, but where it stands in the endless rhythm of creation. The sun's story is one of constant change. Billions of years from now, it will exhaust the hydrogen in its core and begin fusing helium instead. As that transformation unfolds, the outer layers will swell outward, growing vast and red, a red giant star stretching beyond the orbit of Mercury and perhaps Venus. The glow will deepen, the surface cool, and the planets will bathe in a dim, crimson light. For Earth, it will be both an ending and a return, our atoms sent back into the cosmic sea from which they came. Yet even in that distant future, the sun's heart will not vanish. Its core will shrink into a white dwarf, still glowing faintly in memory of the light it once gave. Through that slow fading, the universe continues its patient conversation with time. Every element that makes up your body, iron in your blood, calcium in your bones, carbon in your cells, was born in a star that lived and died long before the sun. In their final moments, those ancient giants exploded as supernovae, scattering heavy elements across space. Clouds of that stardust later collapsed under gravity to form new suns, new planets, and eventually, us. The sun itself carries the chemical fingerprints of those older worlds, a living archive of cosmic history. When you touch the Earth, you touch remnants of those ancient fires. When you breathe, you inhale atoms forged in 1,000 vanished stars. We are, quite literally, made of light, condensed into matter fragments of a story that began long before humanity learned to look up. And as we rest beneath that same light tonight, we continue the tale they started. And from the quiet heart of our own sun, we now drift outward into the darkness, toward the first true neighbor beyond home, a faint red star that waits patiently across the gulf of space. Just beyond the reach of our sun's gravity drifts a small, faint red star, Proxima Centauri, the closest known neighbor to our solar system. It lies just over 4 light-years away, a distance so immense that even light takes more than 40 months to cross it. Through a telescope, it appears unremarkable, a dim ember among the southern constellations. Yet in that subtle glow burns a quiet significance. This tiny red dwarf is our nearest step toward the wider galaxy. It's smaller than Jupiter and far cooler than our sun, glowing softly in shades of crimson instead of gold. If you could stand on a nearby world, the sky would never grow bright, only a deep, endless twilight under a star that barely rises. Still, this humble light is the first bridge between our system and the stars beyond. Whispering that distance is only another kind of waiting. Orbiting this faint red star is a planet known as Proxima Centauri b, a rocky world just a bit larger than Earth. It sits within the so-called habitable zone, the delicate band where temperatures might allow liquid water to exist. There, warmth from its small star could create oceans, clouds, and perhaps even a thin atmosphere. Yet this closeness also brings danger. The planet is likely locked in one orientation, one face always turned toward the light, the other forever frozen in darkness. On that narrow twilight ring between day and night, wind could carry warmth and whisper through valleys lit by a dim red sun. It's a haunting image, a world suspended between 2 eternities, forever chasing its own horizon. Scientists discovered this world not by sight, but by the faint tug it exerts on its parent star. Using a technique called radial velocity detection, astronomers watch the light of Proxima Centauri shift slightly as the planet's gravity pulls it to and fro. The effect is almost imperceptible, a wobble measured in meters per second, smaller than a human walking pace, yet it reveals entire worlds across impossible distances. Each oscillation in starlight tells of a planet unseen, orbiting quietly in darkness. From Earth, This method has uncovered thousands of exoplanets, each one a subtle rhythm written in light. The wobble of Proxima's star became a message from across the void, proof that even the faintest suns might hold secrets worth listening to. Life on such a planet would endure a strange balance of light and darkness, because Proxima b likely rotates slowly and is tidally locked. One hemisphere faces its star in endless daylight while the other sleeps in permanent night. The day side would glow beneath a dim red sky, its air stirred by fierce winds flowing toward the frozen dark. Along the dividing line, the terminator could lie a narrow band of perpetual dusk, perhaps the only region gentle enough for water to remain liquid. There, a red sun would hover forever at the horizon, neither rising nor setting, bathing the landscape in an eternal sunset. It's a vision both alien and strangely peaceful, a planet half in fire, half in shadow, yet holding the quiet potential for balance. But even peace is fragile around a red dwarf. Proxima Centauri is restless, prone to sudden flares and radiation storms that can outshine the entire star for minutes at a time. These bursts send waves of charged particles sweeping across space, capable of stripping atmospheres and sterilizing exposed worlds. Instruments on Earth and in orbit have recorded these tempests, flashes of ultraviolet and X-ray light that turn the calm crimson glow into a violent blaze. For any life that might exist there, survival would depend on shelter beneath rock or ocean, a hidden world beneath an unpredictable sky. Still, each flare reminds us how alive the cosmos truly is. Even the smallest star can rage with energy, breathing in fire what our own sun whispers in light. And beyond this quiet storm of crimson, another pair of stars await in the same system, calling us further into the southern sky. Even under the dim light of a red sun, life might still find a way. Some scientists believe that if Proxima b ever had oceans, radiation from its parent star could have pushed potential organisms below the surface, beneath layers of ice and rock. Warmth from the planet's core might sustain hidden seas, protected realms where microbes could drift in the dark, living off chemical energy rather than sunlight. On Earth, life thrives in boiling vents, under polar ice, and in caves sealed for millions of years. Such examples hint that biology doesn't need sunshine, only time and stability. So while the surface of Proxima b may be barren and burned by flares, its interior could hold a different story, a quiet ocean world listening to the heartbeat of a red star above. And if such life exists there, it would prove that survival in the universe is less about light and more about persistence. Proxima Centauri might not be alone with just one planet. Astronomers have found subtle signals that hint at two more Proxima c and Proxima d. These potential companions, farther from the star, are colder and more massive, perhaps resembling icy mini-Neptunes. Their discovery came through long-term observations of the star's faint, repeated motions, each trace suggesting an unseen gravitational partner. If confirmed, it would mean the nearest star system hosts a small family of worlds, orbiting together in the slow rhythm of cosmic time. From Earth, they remain invisible, too dim even for our largest telescopes. Yet in their gravity, we can feel the echo of their presence, a gentle reminder that no world drifts entirely alone. And as our instruments grow sharper, these hidden companions may become the first distant neighbors we truly learn to know. To turn suspicion into certainty, astronomers must watch light with extraordinary patience. Confirming an exoplanet requires more than a single detection it demands. Repeated, consistent signals over months or even years. Scientists combine methods: the radial velocity wobble, the dimming of starlight as a planet passes in front, and subtle timing variations in the star's own pulse. Each technique is like hearing a faint heartbeat beneath the hum of the universe. Instruments such as the European Southern Observatory's HARPS and NASA's TESS refine those rhythms into clear proof. When the patterns repeat exactly as predicted, a new world earns its place among the stars. It's a delicate art of listening, of reading the faintest tremors in light. Every confirmed exoplanet is a triumph of stillness and precision, showing that patience can reveal entire worlds hiding in plain sight. The idea of reaching Proxima Centauri has long haunted human imagination. At 4 light-years away, it's impossibly far by today's standards, yet close enough to dream about. The Breakthrough Starshot initiative envisions sending fleets of tiny probes powered by laser sails, each traveling at a fraction of light speed. Such a craft could cross the distance in just 20 years within a single lifetime. They would send back flashes of data, images of alien skies, and perhaps the first real glimpse of another Earth-like world. For now, it's only an idea, but it reflects something deeply human, the urge to touch what we can only see. The first step toward the stars may begin not with a rocket, but with a light sail whispering through the dark, and in that silence, humanity would finally hear its echo coming home. From Proxima Centauri, we've learned that the universe is far more patient and unpredictable than we once imagined. Red dwarfs like it make up the vast majority of stars in our galaxy. Small, dim, and enduring, they burn fuel so slowly that they could shine for trillions of years, long after larger suns have faded. But their tempers are fierce, their flares violent, their light both a promise and a warning. Through Proxima, astronomers study how magnetism and gravity weave together to shape entire worlds. It reminds us that life may need not comfort, but resilience. A red dwarf teaches humility, that brightness is not the measure of significance, and that the quietest lights may be the ones that last the longest. As we leave Proxima behind, the twin stars of Alpha Centauri begin to glow ahead, waiting for us to draw closer through the endless night. In the deep southern sky, 2 bright stars move together in a slow, graceful orbit, Alpha Centauri A and Alpha Centauri B. They are bound by gravity, circling one another every 80 years like cosmic dancers locked in a luminous embrace. A shines yellow-white, much like our own sun, while B glows slightly cooler and orange. Far beyond them, Proxima Centauri drifts as a distant third companion, loosely tethered by the same invisible thread of gravity. Seen from Earth, the pair appears as one sparkling point, the third brightest in the night sky. Through telescopes, however, their separation reveals a harmony older than humanity itself. 2 suns exchanging light, heat, and shadow in perfect rhythm. Their quiet orbit reminds us that not every world travels alone. Some are born within partnerships, carrying the warmth of 2 suns instead of one. And for those who gaze southward, this double glow has guided eyes for millennia. For thousands of years, the twin lights of Alpha Centauri have captured human imagination. To ancient observers in the southern hemisphere, they were symbols of duality, balance, and kinship, written in fire. Indigenous Australians wove them into sky legends as celestial brothers travelling together across the dreamtime. Navigators of the southern seas used their glow to mark direction, calling them pointers, leading the way toward the Southern Cross. Even today, their presence holds a mythic calm, a reminder of companionship across distance. They've become more than stars. They're stories of connection between worlds and between people. In their pale shimmer, sailors saw safety, poets saw longing, and scientists saw the promise of other suns. And now, as telescopes trace their orbit, those same lights still carry humanity's oldest wish that somewhere out there, under another sky, another home might be waiting. Binary stars like Alpha Centauri teach us how relationships shape creation itself. Two suns orbiting each other create shifting fields of gravity that sculpt the space around them. Planets forming within such systems must navigate these competing pulls, finding orbits that remain stable over eons. Too close to one star, and a planet risks being torn apart. Too far, and it may drift into the cold between. Yet stability can arise in surprising ways through resonance, balance, and rhythm. Astronomers use simulations to understand how these worlds might dance between two suns, experiencing twin dawns and double shadows. Such systems challenge the imagination of what a habitable world might look like. Skies glowing with two lights, overlapping seasons, complex tides. And though the physics is intricate, the beauty is simple. Gravity itself becomes a conversation between partners, endlessly shaping what may someday become life. Within this double system, there are regions where temperatures could support liquid water, the so-called habitable zones. Alpha Centauri E, being slightly larger and hotter than our Sun, would host a band farther out, while B's cooler glow brings its zone inward. In theory, rocky planets could orbit stably around each star, warmed gently by both lights. From such a world, dawn would begin with one sun rising and end with another, sinking behind distant hills. The two stars would never stray far from each other in the sky, painting every night with golden and amber hues. For scientists, this is more than a poetic image. It's a laboratory of possibilities. If life can exist in a system of two suns, it means nature's tolerance is broader than we dreamed. And somewhere in that warmth, we might glimpse the first true twin to our own Earth. In the early 21st century, excitement swept through the scientific community when data suggested a planet orbiting Alpha Centauri b, an Earth-sized world in a possible habitable zone. Telescopes recorded tiny shifts in starlight, hinting at the familiar pattern of a planet's pull. The news sparked headlines and hope, but as more precise instruments followed up, the signal faded. It had been noise, not a world, a false planet alarm born of wishful measurement. Still, the search did not end there. Each refinement in technology brings the twin stars into sharper focus, promising one day to confirm what we've long suspected. The void around Alpha Centauri may not remain empty forever. Every mistaken signal, every quiet night of observation brings us closer to truth. And as the data clears, the next discovery may finally reveal a real Earth orbiting just beyond the glow of our nearest twin suns. If you could stand on a planet circling one of the Alpha Centauri stars, the sky above would be both familiar and wondrously strange. Two suns would share the heavens, one golden and bright, the other smaller and tinted amber. Days would shimmer with overlapping light, and nights would never be entirely dark. When the suns drift apart in their long orbit, the brighter would cast long twin shadows, while the fainter one painted the horizon in perpetual dusk. The Milky Way would stretch across the sky, but our sun would appear only as a pale dot among countless others, a distant lantern in the sea of stars. Storms might sparkle under double rainbows, and sunsets could unfold in layers of gold and crimson. It would be a world lit by companionship, where warmth and colour blend into endless twilight. And somewhere above that horizon, Earth would gleam faintly, a reminder of how far home really is. For decades, humanity has dreamed of visiting the stars nearest to us, and Alpha Centauri remains the most tempting destination. The Breakthrough Starshot initiative is our boldest plan, yet a vision of sending tiny probes, no larger than a postage stamp, pushed by powerful lasers to 1/5 the speed of light. These miniature explorers could cross the 4-light-year gulf in just 20 years, capturing images and data before transmitting them home. No human ship could match their speed. But the technology represents the first realistic attempt to reach another star within a lifetime. Idea, test, and failure brings us closer to turning that dream into motion. When the first faint signal returns from Alpha Centauri, it will carry more than data. It will carry the echo of every gaze that ever looked up and wondered what lies beyond the sun. Alpha Centauri's brilliance has made it a favorite subject for astronomers for centuries. Its proximity and brightness allow precise study. Its light is strong enough to reveal the chemical fingerprints of its atmosphere and surface layers. By examining those spectra, scientists can compare its composition to our sun's, learning how different stellar materials create variations in color and luminosity. Its twin nature also offers a natural laboratory for understanding how stars exchange mass, how magnetic activity changes over time, and how gravitational interplay affects stability because it shines so clearly. Alpha Centauri helps refine the very measurements we use to gauge distance and brightness across the cosmos. In that radiant glow lies a benchmark for stellar physics, a candle against which we measure all others. Each observation teaches us not just about those stars, but about the fundamental language of light itself. A triple star system like Alpha Centauri holds a quiet wisdom about balance and endurance. 3 stars bound together in gravity form a stable yet delicate arrangement, a cosmic family that must constantly adjust its rhythm to remain whole. A and B orbit closely, sharing warmth and light, while Proxima drifts far beyond, circling at the edge like a patient wanderer. This structure shows astronomers how gravitational harmony can persist across vast scales. It's a reminder that even in the immense emptiness of space, relationships shape stability. Every planet, every orbit, depends on unseen cooperation. Through Alpha Centauri, we see the elegance of celestial partnership, how multiple stars can coexist without chaos, creating a system both dynamic and enduring. And in that harmony, we recognize our own search for balance, the need to find connection even across distance. Throughout history, Alpha Centauri has symbolized the horizon of human longing, the nearest step toward infinity. From the first sailors who charted its glow to the scientists designing light sail probes, it has been a beacon for curiosity itself. To reach it would mean crossing not only space but imagination, proving that the boundary between dream and reality can be measured in light years. Every generation looks up and finds that same spark, a reminder that the universe is not closed to us but waiting. The twin suns have become more than stars. They are promises written in fire, calling us forward. Someday, perhaps, a tiny craft or a human eye will see their dawn up close. And in that moment, we'll know the ancient hope was justified. Beyond them, endless darkness remains, and beyond that, the next light waiting to be found. In 1916, American astronomer Edward Emerson Barnard peered through his telescope and noticed something strange. Among the countless fixed points of light, one faint red star appeared to shift position against the background sky. Year after year, its movement was undeniable, a tiny wanderer slowly crossing the heavens. Barnard's discovery revealed the closest known star system of its time, a quiet ember, only 6 light-years away. Unlike the blazing giants of the constellations, this one was humble, small, and easily overlooked, yet its subtle motion made it extraordinary. Proof that the stars were not eternal fixtures, but travelers in their own right. For a moment, humanity glimpsed the galaxy in motion, a living ocean rather than a painted dome. Today, that same star still drifts steadily across space, carrying Barnard's name and our continuing fascination with how even the faintest light can teach us something about movement, time, and patience. Barnard's star holds a record that few others can match. It's the fastest moving star in our sky. Every year, it slides the width of a full moon across the celestial backdrop, racing sideways through space at more than 140 kilometers per second. To the naked eye, it's invisible, but sensitive instruments can trace its journey like a heartbeat across the centuries. Its speed is a reminder that the galaxy itself is alive, its members orbiting the center like dancers in slow motion. For astronomers, this rapid motion offers a chance to study stellar dynamics in real time, a nearby traveler showing how gravity shapes the Milky Way's restless currents. In just a few thousand years, Barnard's star will edge slightly closer to us, coming nearer than any known star today. And though its pace is silent, each step brings us closer to understanding how stars migrate through the endless dark. To measure a star's motion across the sky, scientists rely on an exquisite form of geometry known as proper motion. By comparing photographs taken years apart, they track how far a star shifts relative to distant background galaxies. The difference is often minute fractions of an arcsecond, the width of a coin seen from miles away. Barnard's star, however, moves enough to be noticed easily through time-lapse imaging, making it a textbook example of how motion betrays proximity. The closer a star is, the faster it seems to drift. This technique, refined over decades, helps astronomers map the invisible architecture of the galaxy, tracing how stars orbit, scatter, and migrate. Proper motion turns the night sky from a still image into a living film, one frame at a time. Watching Barnard's star move reminds us that nothing in the cosmos truly stands still. Even the quietest light is on a journey of its own. Barnard's star is a red dwarf, one of the smallest and coolest types of stars in existence. It contains only about 1/6 the mass of our Sun and shines faintly. A deep ruby ember glowing at the edge of visibility, its surface temperature barely reaches 3,000 degrees Celsius, giving off light so weak that no human eye could ever see it unaided. Yet beneath that modest exterior lies remarkable endurance. This tiny star could burn for trillions of years, long after our Sun has faded. Its light, though dim, represents stability and time beyond comprehension. Studying it helps scientists understand how such low-mass stars live so efficiently, fusing hydrogen slowly in quiet harmony. In many ways, Barnard's star is a symbol of cosmic humility, small, enduring, and patient, and in its faint radiance, we glimpse the kind of universe that will remain when all brighter stars have gone dark. In the 1970s, a wave of excitement swept through astronomy when several researchers claimed to have discovered planets orbiting Barnard's star. Using delicate measurements of its position, they believed they saw a rhythmic wobble that hinted at unseen companions tugging at the star. Headlines around the world declared the first planets beyond our solar system had been found, but as instruments improved, the signal vanished, an illusion created by the limits of early technology. The so-called ghost planets faded into myth, leaving behind one of science's most famous false alarms. Yet those mistakes paved the way for modern exoplanet detection methods, refining our precision and patience. The hope that began with Barnard's star didn't die. It evolved. Decades later, with new telescopes and instruments, astronomers would return to this same faint red ember, and this time, what they found would change the story forever. More than 40 years after the false alarms of the 1970s, technology finally caught up with hope. In 2018, astronomers using the European Southern Observatory's HARPS spectrograph detected a real planet circling Barnard's star. The signal was faint but consistent, a world about 3 times the mass of Earth. Orbiting once every 233 days, they named it Barnard's Star B, a frozen super-Earth where surface temperatures likely fall below -150 degrees Celsius. It lies just beyond the star's faint glow, wrapped in eternal winter. But its discovery proved that even old, quiet stars can harbor planets. For scientists, it was a quiet victory decades in the making. Confirmation that persistence pays off. And for dreamers, it was a spark, a reminder that the first exoplanet known around our nearest solitary star might be only the beginning of a larger, colder story still waiting to unfold. Though Barnard's Star B is locked in freezing darkness, some scientists wonder whether warmth could linger below its surface. If the planet holds a rocky core rich in radioactive elements, that internal heat might sustain a layer of liquid water beneath thick ice, a subsurface ocean similar to Europa or Enceladus in our own solar system. There, shielded from radiation and cosmic cold, life could persist quietly, feeding on chemical energy instead of sunlight. It's a fragile possibility, but one that changes how we imagine habitability. Life may not need sunshine, only shelter and time beneath miles of frozen crust. Microbes could drift through a silent ocean warmed by the heart of a dying world. And if such life exists, it would mean the universe grows life, not just in warmth and light, but in endurance and patience. Projects inspired by curiosity continue to look toward this faint star. The Breakthrough Starshot initiative, designed to send tiny laser-propelled probes to Proxima Centauri, could one day redirect toward Barnard's star as well. These spacecraft, no larger than a chip, would travel at a fifth the speed of light, crossing the 6-light-year gulf in only 30 years. Their cameras and instruments would capture close-up images of Barnard's system to revealing details no telescope on Earth could see. It's a bold vision, not one of rockets and astronauts, but of intelligence traveling on sails of light. For the first time, humanity might witness another sun up close, a red ember glowing in the cold void. And in that encounter, we'd be meeting both the future and the past, the oldest nearby star touched by the youngest species capable of reaching it. Barnard's star glows dimly, but its longevity borders on eternity. As a red dwarf, it fuses hydrogen so slowly that it will remain stable for trillions of years, hundreds of times longer than the lifespan of our sun. While massive stars blaze briefly and die in violent explosions, Barnard's kind endure quietly. Wasting nothing, studying it helps astronomers understand the future of the galaxy itself, a time when bright stars fade and only red dwarfs remain, illuminating an older, quieter cosmos. In that far future, light will be scarce. Yet, these patient embers will still warm their unseen worlds. Barnard's star shows that endurance, not brilliance, defines cosmic survival, and in its faint glow, we see the shape of eternity, a universe still alive, long after our own sun has turned to ash. Thousands of years from now, Barnard's star will draw closer to Earth, becoming our nearest stellar neighbor. By the year 11,800, it will shine brighter than any star in the current northern sky, perhaps visible even to the naked eye. Imagine our descendants looking up from a changed world, knowing that this tiny red wanderer has finally approached after ages of silence. Their telescopes might reveal its planets in vivid detail, and perhaps even cities of light orbiting under its dim sun. For them, Barnard's star would no longer be a mystery, but a destination, a marker of how far humanity has come. Each generation will inherit that motion across the sky, a promise carried by the slowest traveler, and when it finally glows overhead, those watching may remember us, the ones who first noticed its journey through the dark. For centuries, Wolf 359 hid in plain sight, less than 8 light-years away yet completely invisible to the unaided human eye. Early astronomers charted the heavens with remarkable precision, but this dim ember escaped every catalogue until 1919. The reason was simple: it shines at a magnitude so faint that no telescope of its era could easily catch it. When German astronomer Max Wolf finally detected its slow drift across photographic plates, he uncovered one of the nearest stars to our sun and one of the faintest known. Its discovery revealed that our cosmic neighborhood is full of unseen suns, glowing too softly for ancient eyes to ever notice. Wolf 359 became a reminder that even close to home, the universe keeps secrets in plain darkness. And sometimes, the most ordinary patches of sky can hold invisible neighbors, patiently waiting for humanity's gaze to sharpen enough to find them. The faintness of Wolf 359 exposes the limits of human perception. Under the clearest skies, an unaided eye can see stars up to magnitude 6. Yet, Wolf 359 shines at magnitude 13.5, 600 times dimmer than the threshold of visibility. To detect such faint light requires long exposures and precise instruments capable of collecting every whisper of a photon. For ancient observers, the star simply didn't exist. It lay beyond biology's reach. Even today, it remains invisible except through telescopes, glowing like a tiny ember in Leo's constellation. This extreme dimness teaches astronomers how incomplete our senses truly are, that the night sky we see is only a fragment of reality. Behind the glitter of bright constellations lies an ocean of faint red suns, each with its own worlds and stories hidden beyond sight. Our eyes see the showy few, but our tools reveal the quiet majority. Wolf 359 burns just above the lower boundary of what can be called a star, containing barely 9% the mass of the Sun. It fuses hydrogen into helium at a rate so slow it could be mistaken for stillness. Were it any smaller, it would have failed to ignite fusion altogether and become a brown dwarf, a failed star glowing only from residual heat. But Wolf 359 made the cut, achieving the delicate balance between gravity and pressure that defines true starlight. In its tiny core, Hydrogenatoms collide under immense pressure, releasing just enough energy to keep it alive for trillions of years. To the universe, it's a whisper of light, but one that will outlast every giant sun blazing today. In that quiet persistence lies the miracle of stellar physics, the moment when matter becomes light, and even the smallest flame joins the cosmic fire. While massive stars, live, fast, and young, red dwarfs like Wolf 359 are the patient keepers of time. They consume their hydrogen with exquisite thrift, stretching their lives into spans trillions of years long, longer than the universe has yet existed. When our sun and all stars like it have long since turned cold, red dwarfs will still glow faintly in the dark, sustaining any surviving planets with gentle warmth. Their slow fusion ensures no grand finale, no explosion, just an endless fading into blackness. Eventually, they will cool into invisible remnants called black dwarfs. Theoretical objects the universe is still too young to contain. Wolf 359 offers a glimpse of that far future, a preview of the quiet cosmos yet to come where light grows sparse. But endurance remains éternelle. Wolf 359 may be faint in reality, but in imagination it burns bright. It became famous through science fiction, most notably in the Star Trek universe, as the site of a devastating battle against the Borg, a story of loss and resilience that turned this invisible star into a symbol of struggle and renewal. Fans around the world know its name, even if they've never seen its light. Proof that meaning doesn't require brightness. Fiction gave this obscure red dwarf a voice, transforming astronomical data into myth. The real Wolf 359, however, remains perfectly calm, burning slowly in the dark. Unaware of its fame, it reminds us that stories can bring the cosmos closer, that even a hidden ember in the void can become a legend in the human imagination. Somewhere in Leo's silent patch of sky, that legend still glows unseen, carrying both science and story across the night. Red dwarfs like Wolf 359 teach us that the universe values longevity more than brilliance. These tiny suns, with their cool temperatures and slow-burning hydrogen cores, are built for eternity. A red dwarf can shine for up to 10 trillion years, hundreds of times longer than our sun's entire lifespan. That means long after galaxies change shape and most bright stars fade, red dwarfs will still glow, carrying their planets through cosmic night. They show that life and stability may not belong to the brightest, but to the most enduring. Astronomers often say that if the universe has a final chapter, it will be written in the red light of these patient stars. In their small, steady hearts lies the secret of survival, quiet endurance in a universe that never stops moving. And perhaps, in that persistence, we glimpse how the cosmos itself remembers to last. Searching for planets around faint red dwarfs demands remarkable sensitivity. Because their light is so weak, even the smallest disturbance can hide or distort a planetary signal. Scientists rely on indirect clues, the wobble method, which measures how a planet's gravity tugs its star, and the transit method, which tracks tiny dips in brightness when a planet passes in front. Both require long observation times and instruments capable of detecting minute shifts in light and motion. Around stars like Wolf 359, each photon counts. Years of patient watching might reveal a single wobble or dimming the signature of an unseen world. It's a slow form of discovery, guided not by spectacle but by precision. Through these faint beacons, we learn to see the invisible, turning silence itself into data. Every discovery begins as a whisper barely above the noise, teaching science the art of listening deeply. Despite decades of searching, many of the nearest red dwarfs likely still hide unseen worlds. Their faint light and restless flares make detection difficult, concealing planets that might orbit quietly just beyond our reach. Some could be frozen globes, others oceanic worlds warmed by internal heat. A few may even exist within the fragile balance of a habitable zone, where liquid water can survive. The challenge is that these planets produce signals so subtle they blend into the background hum of starlight. Yet every year, improved telescopes sharpen our view, revealing more of what was once invisible. The unseen worlds remind us that discovery is not about having looked, but about looking better. Somewhere among the faint red embers of the nearby sky, entire systems wait patiently to be found, circling suns so dim that even their light struggles to cross the dark. If life exists elsewhere, the odds favor red dwarfs. They make up 75% of all stars in the Milky Way, and most appear to host planets, some rocky, some warm enough for liquid water. While their dim light might seem inhospitable, it also offers stability. Red dwarfs change little over trillions of years, providing steady energy for unimaginable spans of time. Civilizations born around them could thrive long after brighter worlds have gone dark. These small stars may be the cradles of life in the deep future, when our sun is only a memory. The quiet red glow could light the next wave of biology, evolution, and awareness. In that sense, red dwarfs represent continuity, the promise that the story of life may continue long after humanity's chapter closes, and their silent persistence may hold the key to cosmic immortality. Wolf 359 leaves us with a lesson deeper than astronomy. Its darkness is not emptiness, but patience, a quiet example of how the universe endures through time, too vast to imagine. It doesn't blaze, it doesn't demand attention, yet it survives when all else fades. In that persistence, there's a reflection of life itself, the slow unfolding of existence through calm and endurance. When we gaze at the night sky, it's easy to love the bright stars that draw the eye. But the real strength of the cosmos lies in the faint ones, the unseen majority that keeps burning softly through the eons. Wolf 359 is one of them, a humble point of light that teaches us to value stillness. And as we drift onward to the next star, its quiet glow reminds us that sometimes the smallest lights last the longest. For ancient civilizations, Sirius was more than a star, it was a messenger. The Egyptians called it Sopdet and watched for its first appearance in the dawn sky each summer, an event that foretold the flooding of the Nile. That flood brought fertile soil and life itself to the desert. So Sirius became a symbol of renewal, of time's sacred rhythm. To the Greeks, it was Serios, meaning scorching, a fiery herald of the year's hottest days. Mariners and priests alike built calendars around its rising. Long before telescopes, humanity learned to live by the pulse of the stars, and none burned more faithfully than the dog star. Even now, As its blue-white light reaches us across 8.5 light years, we're seeing the same glow that guided farmers and dreamers thousands of years ago. Sirius connects every age through a single beam of light. When the Nile rose and the river valley bloomed, the Egyptians knew that Sirius had returned to the dawn. They recorded its appearance with meticulous precision, marking time not by seasons or rulers, but by its rising, the heliacal event that defined their year. The floodwaters would arrive days later, proving that the heavens spoke through this brilliant star. Across generations, it became a sacred clock, linking earth and sky. Other cultures echoed this reverence. To the Polynesians, it guided ocean voyages. To the Chinese, it was the celestial wolf. To the Romans, the heart of the dog days when the heat grew relentless. Though our modern world no longer looks to Sirius for harvests, its story remains one of dependence and awe. Even now, scientists measure its cycles not to plant crops, but to calibrate instruments, yet the rhythm it set still governs human curiosity. For centuries, Sirius appeared as a single, blinding point of light until the truth emerged. It's a binary system, the dazzling primary. Sirius A shines 25 times brighter than the sun, while its faint companion, Sirius B, hides in its glare. They orbit each other every 50 years, separated by distances that shift between 8 and 31 astronomical units, a cosmic duet of brilliance and shadow. Sirius A is young and massive, twice the sun's size. Its searing white light, born from a surface hotter than 9,000 degrees Kelvin. But Sirius B is a ghost, the collapsed core of a once great star that burned through its fuel and died. Together, they embody stellar evolution itself, life and death bound in gravity's dance. For astronomers, Sirius isn't just beautiful, it's a living textbook of how stars live, and continue in altered form. The story of Sirius B reveals the strange physics of white dwarfs, where matter itself resists, collapse through quantum rules. When the parent star exhausted its hydrogen, gravity crushed its core until electrons packed so tightly that they could move no closer, a condition called electron degeneracy. That invisible pressure now holds the star up against its own gravity. The result is astonishing: a sun's worth of mass crammed into a sphere no larger than Earth, a teaspoon of its material weighing tons. Sirius B no longer burns fuel, it simply radiates leftover heat, glowing faintly for billions of years. This was one of the first proofs that stars can die quietly, leaving behind dense embers instead of fiery destruction. Its existence helped redefine stellar physics forever, showing that even in death, a star can still shine dimmer, smaller, but impossibly enduring. In 1862, American telescope maker Alvin Clark peered through a new lens he'd just completed and saw something no one else had ever witnessed: a tiny, faint star next to Sirius A. That small light confirmed a prediction made nearly 2 decades earlier by German astronomer Friedrich Bessel, who had noticed Sirius wobbling in its motion and reasoned an unseen companion must exist. Clark's discovery of Sirius B proved that mathematics and observation could reach beyond sight itself, a triumph of reason over distance. The two stars now stood as evidence that the cosmos held invisible partners waiting to be revealed. Clark's moment marked not only a milestone in astronomy but a turning point in human perception, proof that the universe hides entire stories behind its brightest lights. And as we prepare to follow Sirius deeper into its mysteries, that discovery still shines, like the beginning of a greater revelation yet to come. If you could stand on a planet orbiting Sirius A, the sky would blaze with light beyond imagination. The primary star would shine twice as large as our Sun and far brighter, bathing the landscape in icy white radiance. At night, Sirius B would rise a tiny blue-white gem, brighter than any full moon seen from Earth, casting shadows of its own. Together, they would create a sky of twin lights, one warm and commanding, the other sharp and ghostly. The double shadows would shift and stretch as the two stars moved through their 50-year orbit, painting time itself across the terrain. Nights would never be truly dark, and dawn would come from two horizons. For any world fortunate enough to exist there, the concept of day and night would blur into something alien and beautiful, a perpetual shimmer between light and light. And yet, no such planet has been found, only our imagination circling that brilliant pair at the heart of every white dwarf. Physics takes on a strange, quantum form of defiance. Crushed under immense gravity, atoms lose their individuality. Their electrons pressed so tightly together that they create a new kind of pressure, one not born of heat, but of quantum rules. This is electron degeneracy pressure, a phenomenon that resists further collapse, even when temperatures plummet. It keeps Sirius B stable, preventing it from becoming a black hole despite its enormous density. Each electron acts as if declaring that no two particles can share the same quantum state, locking the entire star in a silent standstill between gravity and resistance. In that stillness lies an eerie beauty, a corpse of a star held in perfect balance, glowing from residual heat that will take billions of years to fade. It's not alive, but it endures proof that even death can obey elegant laws. Ancient observers once described Sirius as red, a mystery that puzzled astronomers for generations. Today, we see it as fiercely white-blue. So, why the difference? Some speculated that Sirius B might have been a red giant in the distant past, its dying glow tinting the system crimson before collapsing into a white dwarf. But stellar models show that transformation happened over 100 million years ago, long before humans ever looked up. Others blame atmospheric distortions, translation errors, or the shimmering effect when the star hovers near the horizon. Whatever the reason, those ancient records remind us how human perception can change with time and language. The universe remains the same, but our view of it evolves. Sirius hasn't altered color in our lifetime, we have. Every era sees the cosmos through its own eyes, and each description, red or white, tells us as much about humanity as it does about the stars. Could a habitable planet survive in the Sirius system? The answer lies in the balance between light and chaos. Sirius A is twice as massive as the Sun and 25 times brighter, meaning its habitable zone would sit far away, perhaps 2 to 3 astronomical units out. A world there would orbit in warmth similar to Earth's, though bathed in harsher ultraviolet light. But the presence of Sirius B complicates everything. When it became a red giant, its expanding outer layers could have destabilized or destroyed any inner planets. Gravitational tides and radiation bursts might have stripped atmospheres clean. If any planets remained today, they would circle far beyond the chaos, in wide, cold orbits, frozen but stable, yet in the vast timescales of stellar rebirth. New planets could form from debris rings left behind. The Sirius system is both a warning and a promise that creation and destruction often share the same orbit. far into the future, long after Earth's continents have vanished and the Milky Way has merged with Andromeda, the twin stars of Sirius will fade. Sirius A will expand into a red giant, then shed its outer layers, becoming another white dwarf beside its ancient companion. The two remnants will orbit one another quietly, twin embers cooling through eternity. No planets, no light, just the soft whisper of fading heat radiating into the dark. In that distant era, when the cosmos grows cold and sparse, even these white dwarfs will dim into blackness, their energy spent. Yet, their story will remain written in the atoms scattered across space, the same atoms that once burned bright and gave life to calendars, myths, and dreams on Earth. And as the universe drifts towards silence, the memory of Sirius will still shine in the minds that once looked up and called it home. Ross 128 glows quietly in the constellation Virgo, a red dwarf, unlike its tempestuous cousins. While most stars of its kind erupt with violent flares that could strip a planet's atmosphere bare, Ross 128 remains calm and steady, burning hydrogen with gentle persistence. That stillness makes it special, a red dwarf that offers light without destruction. Its energy output may be small, only a fraction of the sun's, yet it never lashes out with the chaos that makes many nearby stars hostile to life. Astronomers call such stars inactive, a rare blessing in a galaxy dominated by restless fires. In that steady glow, planets can orbit safely for billions of years, their skies unscarred by radiation storms. Ross 128 is not famous for brightness, but for serenity. And that calm has made it one of the most hopeful places in the search for life beyond Earth. In 2017, astronomers discovered a planet orbiting this quiet star Ross 128b. Using the radial velocity method, they detected the faint wobble of the star caused by the tug of an orbiting world. The measurements revealed a planet about 1.4 times the mass of Earth, circling its star every 9.9 days. Despite being so close, it lies within the habitable zone thanks to the star's dim light. Ross 128b receives roughly the same warmth Earth does, suggesting temperatures that could allow liquid water. The planet doesn't transit its star from our viewpoint, so we can't yet observe its atmosphere directly, but its existence alone was enough to ignite imagination. A stable, nearby world orbiting a peaceful red dwarf, it became a symbol of quiet possibility, of a haven in a galaxy filled with storms. Ross 128's greatest gift to its planet may be its consistent light. Unlike active red dwarfs that bombard nearby worlds with flares, this star's brightness barely changes. That stability gives any potential atmosphere a chance to survive for billions of years. Without constant blasts of radiation, molecules like carbon dioxide, nitrogen, and water vapor could linger instead of being stripped away. If Ross 128b has managed to keep such an atmosphere, it might support clouds, wind, and perhaps even oceans beneath them. Astronomers hope future telescopes, like the James Webb or the upcoming Extremely Large Telescope, will capture enough starlight passing through its edges to detect chemical fingerprints of life. For now, Ross 128b remains an unopened letter, a world we can see but not yet read, suspended in the quiet glow of its patient star. On Ross 128b, one side always faces the star in eternal daylight, while the other lies in endless night. Between them lies the terminator zone, a twilight band where warmth from the day side meets the chill of the dark. This narrow region might offer the most comfortable conditions, where temperatures hover near the point of balance. If the planet has an atmosphere, winds could circulate heat evenly, softening the extremes and creating a ring of perpetual dawn. There, alien clouds might drift through dim red skies, and landscapes could exist in eternal glow. Some scientists believe such twilight zones could be prime habitats for life, stable for billions of years. On a tidally locked world, life wouldn't follow our cycle of day and night. It would evolve in rhythm with eternal light and shadow, perhaps under that fixed crimson sun. A world waits quietly for us to notice. If photosynthesis exists on Ross 128b, it would unfold under red light rather than the full spectrum of our sun. Plants, if they evolved there, might be black instead of green, absorbing every possible wavelength to survive in the dim glow. The slow, steady rays of a red dwarf could sustain life that moves patiently, growing through centuries instead of seasons. Photosynthesis might be less efficient but more enduring, adapted to a world where nothing rushes. On Earth, green reflects the abundance of sunlight. On Ross 128b, black would be the color of hunger and persistence. Such speculation reminds us that life may not need familiar colors or rhythms, only energy, chemistry, and time, somewhere beneath that tranquil red sky. If life has taken hold, it may already be thriving quietly, unseen but unstoppable, nourished by the faint pulse of a star that never rages. In 2017, the Arecibo Observatory detected a strange burst of radio signals from the direction of Ross 128. The transmissions came in unusual patterns, repeating at steady intervals across several frequencies. For a brief moment, scientists wondered if they'd found something extraordinary, perhaps a sign of intelligent life. The story raced through headlines, stirring both excitement and skepticism. Weeks later, the mystery unraveled. The signals came not from the distant star, but from Earth's own satellites orbiting high above, their transmissions bouncing into Arecibo's receiver at the perfect angle. The discovery proved once again that the universe is patient with our curiosity, even when we misinterpret its silence. Yet that false alarm left a mark on history. It reminded humanity that our hope to hear another voice among the stars runs deeper than logic. It's a reflection of our own longing to not be alone. Ross 128 teaches something profound through its calmness. While other stars scream with flares and chaos, this red dwarf simply endures, quietly illuminating its small corner of space. That stability offers a model for life itself, the strength found not in force, but in steadiness. Astronomers often chase explosions, novae, and dying suns. Yet Ross 128 draws attention precisely because it does so little. Its silence becomes a virtue, its reliability a kind of grace. In its unchanging glow, we see a mirror of patience, a universe reminding us that survival often belongs to the quiet. For planets orbiting such stars, peace is not absence, it's possibility. The absence of violence is the space where life might begin, and somewhere in that stillness, something extraordinary could already be breathing. Quiet red dwarfs like Ross 128 are more than astronomical curiosities. They may be the great homes of life in the far future. Their gentle light lasts for trillions of years, giving evolution nearly endless time to unfold. For every massive star that burns out in a few million years, There are countless red dwarfs that will shine long after the galaxies have aged. Their long lives create stable conditions, protecting planets from the violent outbursts that plague larger suns. In the grand story of the cosmos, the bright stars are brief chapters, but red dwarfs are entire volumes steady, enduring, patient. They remind us that habitability is not just about distance or warmth, but about time. The universe rewards persistence, and these faint embers may be where life writes its longest chapters. Someday, when our own sun fades, their light will still burn. Ross 128 is slowly drifting closer to us, moving through space at about 31 kilometers per second. In roughly 79,000 years, it will overtake Proxima Centauri and become the nearest star to our solar system. For future astronomers or perhaps future civilizations, it will shine as our new cosmic neighbor. That closeness will make it one of the best places to study exoplanets directly, to analyze their atmospheres and maybe even glimpse their surfaces. By then, humanity might have colonies on Mars or ships capable of reaching nearby stars. The approach of Ross 128 symbolizes time's slow dance, where even stars migrate across the galaxy. For now, it drifts quietly toward us, its light unchanged for millennia. One day, when it becomes our closest sun, it might no longer be just an object of study, but a destination far into the future. When humanity finally spreads beyond Earth, the worlds around stars like Ross 128 may become our new homes. Beneath a red sun, days would never be blinding, only softly lit in hues of amber and wine. Shadows would stretch long and slow, and life would move to gentler rhythms. Crops might grow under dim skies, adapting to the deep crimson light. Cities could rise in perpetual twilight, powered by the energy of a calm star that will never die in human timescales. To live there would mean learning to love quiet light, an endless dusk to find beauty in slowness and survival in stillness. Perhaps, in that distant age, Ross 128 will not just be a point in the night sky, but a sanctuary for future generations, glowing like a promise kept across the light years. 3 out of every 4 stars in the Milky Way are red dwarfs, tiny suns that glow faintly and live unimaginably long lives. Their small size means they burn fuel slowly, never shining as bright as stars like our sun. Yet their abundance fills the galaxy with quiet light. Because they're so dim, most can't be seen without telescopes, but they form the unseen backbone of our cosmic neighborhood. Each one may host planets, many within zones warm enough for liquid water. Red dwarfs may not dominate the night sky, but they dominate existence itself. Their subtle glow outnumbers brilliance 1,000 to 1, proving that the universe favors endurance over spectacle. To the naked eye, the heavens appear filled with bright stars, yet behind them lies a hidden ocean of faint red fires, the true majority of creation. And it's among these countless quiet suns that the future of life in the cosmos may already be taking shape. Astronomers classify stars by their light, sorting them into a sequence that tells their story: O, B, A, F, G, 2K, and M. The hottest and most massive, the O and B types, blaze blue-white and live only millions of years, while the M class marks the smallest, coolest red dwarfs that can burn for trillions. Our sun sits near the middle, a G-type star balanced between brilliance and longevity. The sequence is more than an alphabet. It's a timeline written in color and temperature, revealing how matter evolves under gravity's pull. Each spectral class represents a different pace of life in the universe, from furious bursts to quiet endurance. Red dwarfs at the end of that scale show that the cosmos doesn't always rush, it often whispers. And in that whisper, we hear the patient rhythm of creation itself, slow and enduring as the stars. The color of a star reveals its temperature, a natural code written in light. Blue stars are the hottest, reaching tens of thousands of degrees, while red dwarfs like those of type M barely pass 3,000. This gradient explains why some stars blaze like diamonds and others smolder like embers. Temperature affects brightness, size, and lifespan. The hotter the star, the shorter its existence. Red dwarfs, cool and efficient, sip their fuel carefully, releasing warmth rather than fire. Scientists use spectroscopy to decode these colors, splitting starlight into rainbows that display chemical fingerprints and energy levels. To the trained eye, a spectrum is a biography, a record of heat, age, and motion. The night sky becomes a gallery of thermal art, every hue a signature of physics in motion. And as telescopes map these subtle shades, we realize that color isn't just beauty, it's knowledge, glowing quietly from the heart of every star. Red dwarfs live slowly, their fusion engines burning with remarkable restraint. Unlike larger stars that consume hydrogen in a few billion years, red dwarfs stretch the same fuel over trillions. Inside them, convection carries heat evenly throughout the core, preventing waste and extending life beyond imagination. This stability makes them nearly immortal on human timescales. When the sun and all bright stars have faded, red dwarfs will still glow, marking the final age of starlight in the universe. Their faint warmth ensures that planets orbiting them could remain habitable for eons, evolving life with patience rather than haste. The universe's future belongs to them, small, quiet, and enduring. Each one is a testament that survival favors balance, not brilliance. The light that endures longest is the one that burns gently, and in that slow fusion, do we glimpse the eternal heartbeat of the cosmos that will one day outlive everything we know. The ancients mapped the heavens with care, but they never saw the majority of the stars that surround us. Red dwarfs, faint and cool, were beyond the reach of unaided sight. To early astronomers, the night sky appeared bright and complete, yet it hid billions of unseen suns. Only with the invention of powerful telescopes in the 20th century did humanity begin to realize that most stars are invisible not because they aren't there, but because their light is too soft for human eyes. These hidden suns changed our understanding of the cosmos entirely. The universe was not made only of fire and brilliance, but of endurance and shadow. The discovery of the red dwarf majority revealed that what's unseen often matters most. Even now, when we look up at the glittering constellations, that we're witnessing only a fraction of the truth, the visible edge of a vast and silent sea of light still waiting to be known. Modern telescopes have finally lifted the veil on the galaxy's hidden majority. Instruments like the Hubble Space Telescope, the Very Large Telescope in Chile, and the Kepler mission have revealed that faint red dwarfs far outnumber the bright stars once thought to define the night. Infrared observatories detect their subtle heat signatures, piercing through dust and distance to expose billions of tiny suns that once went unseen. Each new survey deepens the map of our cosmic neighborhood, showing that the Milky Way is a city of dim embers, not blazing fires. The Gaia spacecraft now tracks their motion with exquisite precision, turning darkness into data. What was invisible to every human who ever looked up is now charted star by star. These discoveries reshape how we view our place in the cosmos. We live not among a few bright giants, but in a quiet ocean of faint, enduring stars, the true citizens of the universe, shining softly for trillions of years. Yet living near a red dwarf would not be easy. Their dim light means any habitable planet must orbit close, so near that it risks being tidally locked, one face scorched in eternal day, the other frozen in endless night. Many red dwarfs also flare unpredictably, releasing radiation strong enough to strip atmospheres bare. Even the calmest among them emit bursts that could erase fragile biospheres. Life there would need to adapt, burrowing underground or beneath oceans, shielded from the star's temper. Photosynthesis would favor darker pigments, absorbing every photon of red light to survive. But where conditions hold steady, even faint warmth might be enough. Scientists believe that if life can adapt anywhere, it can adapt there. Red dwarfs demand patience and resilience, qualities nature already possesses in abundance. Their worlds may not be paradise, but they could be cradles for the universe's most enduring forms of life. Some red dwarfs host entire systems of planets packed closely together, like clockwork mechanisms turning in silence. Worlds, such as those in the TRAPPIST-1 system, orbit within distances smaller than Mercury's path around our Sun, yet remain stable through delicate gravitational balance. From one planet's surface, others might appear huge in the sky, glowing crescents hanging in perpetual twilight. These compact arrangements allow multiple potentially habitable worlds to coexist, warmed gently by a single red sun. Astronomers studying them see echoes of miniature solar systems smaller, dimmer, but no less elegant. They reveal how nature uses gravity and rhythm to craft complexity from simplicity. For explorers of the future, such systems could offer entire archipelagos of worlds, each different, yet bound by the same faint light. And somewhere among them, life might already be waiting, thriving quietly under skies that never truly brighten or fade. The numbers are staggering. Statistically, nearly every red dwarf in the galaxy may host at least one planet, and as many as 1 in 5 could hold an Earth-sized world in its habitable zone. That means tens of billions of potentially life-bearing planets, orbiting stars we cannot see without telescopes. The odds suggest that life, in some form, must exist elsewhere, not rare, but inevitable, even if only a fraction of these worlds sustain it. The galaxy would be alive, with unseen ecosystems. Red dwarfs extend the possibility of life far into the future, offering stability long after larger stars die. For scientists, these probabilities turn wonder into expectation. For dreamers, they turn loneliness into hope. Every faint red dot in the night might hold oceans, mountains, or creatures gazing upward beneath their own dim suns. The silence between stars may not be emptiness. It may be full of listening. When the last bright stars fade and galaxies drift into silence, the red dwarfs will remain. Their slow fusion will continue for trillions of years, outlasting every nebula, every sun, every civilization. They are the keepers of the universe's final light, glowing softly into an age when darkness will rule As time stretches toward infinity, these stars will cool, shrinking into embers, their warmth fading grain by grain. But even then, they'll carry the memory of the cosmos, the last visible proof that creation once burned bright. To witness a red dwarf is to glimpse the farthest future, the universe's heartbeat slowed to a whisper. Long after our world is gone, these quiet suns will still shine over unseen worlds, the final guardians of light, holding vigil until the cosmos itself forgets how to glow, and in that long night, their patience will be the universe's last breath. Epsilon Eridani is one of the youngest nearby stars, a bright orange dwarf only a tenth the age of our Sun. At just 800 million years old, it offers a glimpse of what our solar system might have looked like in its youth. Vibrant, chaotic, and full of debris. Its spectrum and temperature make it a close solar cousin, yet its activity betrays its age. Flares burst across its surface, magnetic fields twist violently, and stellar winds blow with 10 times the strength of the sun's. Around it, dust clouds shimmer where new worlds are still forming. To study Epsilon Eridani is to peer backward in time, toward the adolescence of stars. It shows how planetary systems begin not in peace but in turbulence, where collisions and creation share the same orbit, and somewhere in that cosmic storm, planets are gathering, shaping themselves into the familiar patterns that one day may cradle life of their own. Surrounding Epsilon Eridani lies a broad, bright debris disk, a ring of icy and rocky fragments left over from planet formation. Observations from the Spitzer and Herschel space telescopes reveal two distinct belts, much like our asteroid and Kuiper belts, suggesting a complex planetary system still in the making. Within those rings, countless collisions grind comets and planetesimals into dust, replenishing the disk in a continuous cycle of destruction and rebirth. Gaps in the material hint at unseen planets shepherding the debris, their gravity sculpting the chaos into harmony. This glimpse of a young system reminds us how worlds grow from wreckage, how creation is often messy and slow. The light that glints from Epsilon Eridani's dust is sunlight in its infancy, a reflection of how every world, even ours, once began as fragments adrift in a newborn sea of fire. All planetary systems begin in dust, around young stars. Clouds of gas and particles swirl in a flattened disk, the leftover remains of star formation. Within that haze, grains of rock and ice collide, stick together, and slowly build larger bodies. Over millions of years, they form planetesimals, the seeds of planets, while stellar winds blow away the remaining gas. Gravity takes over, pulling matter into orbits that settle into balance. The process is both violent and delicate. Collisions shatter worlds as often as they create them. Our solar system followed the same path, its planets born from the ashes of failed ones. In observing systems like Epsilon Eridani, astronomers witness the earliest chapters of that story being written again and again across the galaxy. Every mote of dust is potential the beginning of continents, oceans, and perhaps even life. From chaos comes order. From dust comes memory. And from time comes the steady rhythm of new worlds taking shape. In 1838, astronomers measured the distance to the stars for the first time, and the honor belonged to 61 Cygni. Using the method of stellar parallax, Friedrich Bessel recorded how its position shifted slightly against the background as Earth moved around the Sun. The displacement was minute, less than 1/3 of an arcsecond, yet it proved that the stars were not infinitely distant. 61 Cygni, a pair of orange dwarfs, became a milestone in astronomy, transforming imagination into measurable fact. Before that moment, distance in space was poetry. Afterward, it became geometry. The star's slow, proper motion earned it the nickname the Flying Star. Racing across the heavens over centuries, its discovery was more than scientific. It was philosophical, showing that the universe could be understood not by myth, but by measurement. And with that single calculation, the night sky ceased to be unreachable and became a map we could finally begin to read. Far beyond the crowded plain of the Milky Way, in a sweeping orbit through the galactic halo, drifts an ancient yellow star known as the Captain's Star, or HD 122655, estimated to be 11 billion years old. It formed when the universe was young and heavy. Elements were rare. Its chemistry tells the story of creation before the sun, before Earth, before even the spiral arms of our galaxy took shape. This solitary traveler moves with a halo population of ancient stars, looping far above and below the galactic disk. Its stability and age make it a living fossil, a witness to cosmic history stretching back almost to the beginning. Looking at the Captain's Star is like seeing the past frozen in light, a reminder that even in an ever-changing universe, some things endure across eons, and as we turn from youth to antiquity, it bridges time itself, linking the first stars to the worlds yet unborn. Metal-poor stars are time capsules from the early universe, born when hydrogen and helium were almost the only elements in existence. They formed before supernovae had spread heavier atoms like carbon, iron, or oxygen through space. Their faint metallic fingerprints tell astronomers how the first generations of stars lived and died, enriching the cosmos with each explosion. Studying these ancient suns reveals the slow chemical evolution that made planets and life possible. Without those early furnaces, there would be no iron in our blood, nor calcium in our bones, nor carbon in our cells. Every atom heavier than helium owes its origin to stars that came before. In their pale, ancient light, we see the blueprint of everything that followed. These metal-poor relics may be dim and few, but they hold the most profound knowledge that creation is a chain of inheritance, and every living thing is built from the ashes of stars that have long since faded into the dark. From young suns like Epsilon Eridani to ancient wanderers like the Captain's Star, the galaxy teaches through contrast. Youth burns fast, full of storms and energy, while age moves slowly, content in endurance. Young stars show us how worlds begin violent, luminous, and alive with possibility. Old stars show us how time refines and stabilizes what remains. Together, they map the arc of cosmic life, from the first bursts of heat to the long, quiet glow of age. Humanity exists somewhere in between, orbiting a middle-aged star, neither in beginning nor in decline. This duality mirrors our own experience: growth and decay, passion and calm, light and shadow. By studying the stars at every stage, we learn that time is not the enemy of creation, but its sculptor. The universe matures as we do, learning, settling, remembering, and still burning with the quiet hope of what might yet be born. The age of the cosmos shapes where and when life can arise. In its early days, the universe lacked the heavy elements necessary to form planets, oceans, and living chemistry. Only after billions of years of stellar evolution did those ingredients become common. Spreading through galaxies like seeds in the wind, cosmic time itself is the foundation of habitability. It takes generations of stars to build the conditions for biology. Today, we live in a universe mature enough for life, but still young compared to what's ahead. Red dwarfs will glow for trillions of years, offering stable light for civilizations that may come long after us. To understand habitability is to understand patience. The story of life is not a brief spark in time, but an unfolding journey across ages. Every heartbeat, every dawn, every planet is a moment in that grand cosmic calendar still turning through the darkness. Age can be a blessing or a burden, depending on a star's design. Young stars flare and rage, threatening any nearby worlds with radiation and storms. Middle-aged stars like the Sun offer balanced, steady light and stable conditions that allow life to flourish. But with age comes decline. Fuel runs low, gravity tightens its grip, and the star's outer layers expand in fiery old age. Some fade peacefully into white dwarfs, others die spectacularly, scattering new elements into the void. Age means both stability and fragility, creation and decay woven together. For planets, the passage of time is equally double-edged. It allows life to evolve, but it also guarantees eventual loss. In this cosmic balance, time itself becomes the artist and the eraser, drawing beauty only to let it fade. Yet through that cycle, the universe ensures continuity. From the ashes of one sun, another always rises. When astronomers study distant stars, they are really studying the future and past of our own sun. Every type of star reflects a stage our solar companion has passed or will reach. Young, bright systems show us the storms of its birth. Aging red giants preview its final expansion. White dwarfs whisper its long quiet afterward, glowing softly for billions of years. Each observation is a mirror, revealing how universal the process truly is. Our sun is not unique. It is one heartbeat in a vast chorus of light, following the same laws that guide all stars. In seeing others, we see ourselves, transient, luminous, and part of something larger. Even as we look outward, the lesson turns inward that the same fire lighting distant worlds burns quietly within us. And as our sun continues its steady journey through time, it carries the reflection of every star that ever was. Every time you look at a star, you're not seeing it as it is, you're seeing it as it was. Light takes time to travel, and that delay means every beam carries history. The sun's glow reaches us after 8 minutes, Proxima Centauris after 4 years, and the light from distant galaxies may have left before Earth even existed. The farther we gaze, the older the universe appears, a cosmic archive preserved in motion through light. Astronomy becomes the study of time itself. Each photon, a messenger from a vanished moment. What we call the present sky is really a layered past, stretched across space. Even the faintest shimmer from billions of years ago still crosses the darkness to meet us now. We don't simply observe the stars, we listen to their echoes. And in those echoes, we discover that time and distance are not separate things at all, but one continuous fabric woven from memory and light. Relativity teaches us that there is no single now shared across the cosmos. What's present for us may be ancient history for another observer moving at a different speed or living under another gravity. Time stretches and folds depending on motion and mass. So the universe doesn't experience one rhythm, but countless overlapping tempos. Two clocks far apart can never truly agree. This means the stars we see are not just distant in space, but fundamentally elsewhere in time. For travelers crossing light years, present loses its meaning. What's happening here and what's happening there are never simultaneous. The cosmos, then, is not a synchronized performance, but a vast symphony playing in shifting keys. Every particle moves to its own measure. Every atom hums in its own tempo. And as we observe, we realize that even our moment, this instant of awareness, belongs to a timeline seen differently from every corner of the universe. Astronomy is the closest thing humanity has to time travel. With each telescope turned toward the heavens, we look backward through eons, witnessing light that has been on the road since before life began. When we study a distant galaxy, we see it as it existed when dinosaurs walked the Earth. When we gaze deeper, we glimpse the universe only a few 100 million years after its birth. Each photon that reaches us has survived unimaginable distances, untouched, carrying the exact shape of an ancient moment. The night sky is therefore a living museum, where every point of light is an artifact from another age. Unlike mechanical time travel, we can't move ourselves through history, but history comes to us, falling softly through space as starlight. To look up is to look back, to hold in one glance the story of everything that was, and in that backward gaze, we find both humility and wonder. Our galactic neighborhood is far more immense than words can capture. The Milky Way stretches 100,000 light-years across, containing hundreds of billions of stars and perhaps more planets than grains of sand on every beach of Earth. Between stars lies emptiness so vast that even light, traveling at nearly 300,000 kilometers per second, takes years to bridge it. Our sun and its planets drift quietly within a spiral arm called Orion, orbiting the galactic center once every 200 million years. To scale that journey is impossible. If the sun were a single grain of sand, the nearest star would still lie several miles away. And yet, amid this enormity, our solar system is perfectly ordinary. Every patch of the Milky Way holds its own suns, its own worlds, its own versions of us wondering what's beyond. The galaxy is both infinite in scale and intimate in meaning, vast, but somehow still home. The Fermi paradox asks the question that echoes across the stars. If life is common, where is everybody? With hundreds of billions of stars and trillions of planets, logic suggests we shouldn't be alone. Yet space remains silent. Perhaps civilizations rise and fall faster than their signals can travel. Perhaps they choose quiet over contact. Or perhaps the distances are simply too great for communication to bridge. The paradox isn't proof of absence, only a mirror reflecting our own smallness in time and space. Maybe life is rare, or maybe it's everywhere, but hidden, choosing to watch rather than speak. The mystery humbles us, reminding humanity that we've only just begun to listen. Our telescopes, our messages, our curiosity, all are first steps in a conversation that may take millennia to answer. Somewhere out there, the silence could mean solitude, or it could mean we're still waiting for the echo to return. Modern astronomy suggests that our galaxy alone may host tens of billions of potentially habitable worlds. Statistical models from missions like Kepler show that roughly 1 in 5 sun-like stars could have an Earth-sized planet in the right zone for liquid water. Multiply that by the hundreds of billions of stars in the Milky Way, and the possibilities become staggering. Some of these worlds may orbit red dwarfs, basking in dim crimson light, Others may circle brighter suns. Blue skies under twin stars. Most will remain unseen, hidden behind clouds of dust or too distant for our instruments to detect. Yet their likelihood transforms loneliness into probability, the near certainty that life has found other homes beyond Earth. Each world is a coin tossed into the ocean of time, some perhaps already carrying oceans, winds, and the spark of awareness. The silence between stars may not be emptiness at all, but a vast garden still waiting for us to listen more carefully to its living breeze. Dreams of interstellar travel turn imagination into engineering. Concepts like solar sails, propelled by the push of starlight, promise journeys at a fraction of light speed. Using nothing but the universe's own energy, fusion craft could go faster still, harnessing the same reaction that powers the stars to cross light years in decades instead of millennia. Breakthrough starshot in visions, sending gram-sized probes to the nearest systems, tiny messengers riding beams of light. Other ideas explore antimatter drives, warp fields, and generation ships carrying entire societies between stars. Each design begins with the same longing to bridge the impossible, though the distances remain overwhelming. Every advance brings the dream closer, turning science fiction into future possibility. The first true interstellar traveler may not be human, but something we built, carrying our curiosity across the dark. And one day, perhaps, we'll follow, becoming wanderers in the sea of suns. Humanity's story is already stretching beyond Earth. From the first steps on the moon to robotic explorers roaming Mars, we've begun to leave footprints in the wider cosmos. Our satellites orbit every planet. Our telescopes reach the edge of time, and our signals now travel through interstellar space aboard the Voyager probes. Each milestone marks our transition from a planetary species to a cosmic one. The path ahead won't be easy. Radiation, distance, and isolation will test both body and mind. Yet survival has always meant adaptation, and space may be our greatest test yet. In the centuries to come, colonies might rise beneath alien suns, and Earth itself will become our ancestral home rather than our only one. The universe is vast, but not beyond reach. Humanity's expansion into the stars will not just be exploration, it will be continuity. Life, finding new ways to keep the flame burning against eternity. Life and awareness are the cosmos reflecting upon itself. Through consciousness, matter learns to see, to question, to feel. The atoms in our brains were once forged in the hearts of ancient stars. Now they ponder the stars that created them. Science explains the mechanisms, but philosophy reminds us of the wonder that awareness can arise from dust, that curiosity can outlive fear. Every thought, every moment of reflection, is the universe discovering another layer of its own story. When we study the cosmos, we are not separate from it. We are participants in its unfolding. The same energy that fuels the sun fuels our minds, and the same patterns of gravity shaping galaxies guide the chemistry of life. Awareness is not an accident of evolution. It is the natural continuation of creation, the universe learning to recognize its own reflection through living eyes. Perhaps the greatest mystery is that the cosmos knows itself through us. Every observation, every equation, every act of wonder is the universe thinking about its own existence. We are not outside of it, but expressions of it, consciousness, given form in fleeting human shape. The starlight that reaches our eyes completes a circle begun billions of years ago, when those same atoms first burned in a stellar core. To look outward is to look inward, to realize that the boundary between self and space is an illusion made by perspective, humanity's curiosity, our art, our science, all are forms of the cosmos becoming aware of its vastness, even if life fades one day. That awareness will have existed, and that is enough. Through us, the universe has found a way to witness its own beauty. And that simple act makes every moment beneath the stars infinite. Tonight, we've drifted through the quiet corridors of our cosmic neighborhood, from the warmth of our sun to the crimson light of Proxima Centauri, from the icy wanderer of Barnard's star to the calm promise of Ross 128, and onward through the soft embers of Wolf 359 and the blazing beacon of Sirius, each one a world unto itself, each a point of light whispering across time. We've seen young stars still gathering planets from dust and ancient ones carrying memories from the dawn of creation. Together, they form a kind of celestial family, some loud and brilliant, some dim and enduring, all connected by the same light that has touched our world for billions of years. As that light reaches us tonight, it carries not only the story of the stars, but also the quiet truth that we belong to them. Light is more than brightness. It is time itself, traveling endlessly, carrying the history of everything that ever was. The stars we see are not the stars as they are, but as they once were, moments frozen in the vast unfolding of eternity. When we look up, we are not merely observing distance, we are witnessing memory. The glow that warms your eyes tonight may have begun its journey before there were oceans on Earth, or forests, or language. Every photon that touches your skin is a message from the past, a fragment of the universe's story arriving in this single moment of now. In that realization, time softens. The present becomes something vast, something shared with every point of light we've seen. Distance, too, becomes gentler when seen through this lens. The gulf between stars feels endless, yet the same laws of physics, the same elements, the same spark of order that shaped them, shaped us. Every heartbeat is an echo of the same forces that hold galaxies together. Hydrogen became stars. Stars forged elements, and those elements became the atoms of your body. You are not separate from the night sky. You are its continuation. You are stardust, watching stardust shine. And in that unity, the immensity of space becomes less a source of loneliness and more a field of belonging. Across light years, across epochs, the same cosmic pulse moves through all things, steady, slow, eternal. We've wandered through that pulse tonight, tracing the rhythm of existence itself. We've seen stars young and wild, flaring with the energy of beginnings, and stars old and patient, burning softly towards silence. In each, there is a lesson. Youth teaches wonder, age teaches endurance, and between them lies the balance of life. Every star, no matter its brightness, carries its own purpose. Even the faintest glow contributes to the galaxy's harmony. Just as every breath you take adds to the music of the world, we are participants in this vast conversation between light and darkness, creation and rest. As you breathe now, imagine that you are moving with the same rhythm as the cosmos. Your inhale, the drawing of light. Your exhale, the release into quiet space. The stars have been breathing this way for billions of years, expanding and contracting, flaring and fading, and your body carries the same pattern within it. the slow pulse of your heart, the warmth in your chest, the rise and fall of your breath, all mirror the rhythm of the galaxies. You are not an observer, you are a part of the great stillness, the gentle unfolding of time and light. Let that thought bring ease to your mind. Let it loosen the edges of the day and soften the noise of thought. The universe asks nothing of you tonight, not progress, not worry, not words, only quiet awareness. The same silence that rests between the stars exists within you. You've spent the night traveling across billions of years and trillions of miles, yet you never left home. Every journey outward is also a journey inward, toward the space of calm that has always waited behind your thoughts. So, as you settle into rest, remember the truth whispered by every star we've passed, that everything which burns, glows, breathes, and dreams is made from the same ancient fire. The cosmos has spent 13 billion years becoming the moment you are in right now. And in this small, fleeting instant, it is at peace through you. Sleep well under the same sky that connects us to every star we visited tonight. Good night.